Hello everyone. Today we have this cool theorem um, that says that the, the inverse function of A intersect B is equals to the inverse function of A intersect the inverse function of B. So let's begin the proof. First, let's take an arbitrary element in F inverse A intersect B. So take any x in F inverse A union B. So obviously, f of x is in A union B. So by mathematical logic, we can realize that f of x is in A and is very important, f of x is in B, because A union B equals the set as x in um, I forgot it, but let's say R, such that x in A and x in B. And is very important because the union is the same except the and is or. Or let's draw a Venn diagram. A, let's say that A and B, this is the intersect. So obviously, if we take any element of x in here, it's uh, it's in both of them. So and in union A union B, let's draw a Venn diagram. A union B. So if you take any any arbitrary element in it, let's say it's x, so it's either in B or in A. So that is the explanation. So back to the proof. Take any x in F inverse A union B, and F of x in A intersect B. Sorry, I said union. So that's by the definition of intersection, F of x in A and F of x in B. So hence we can realize x in F of inverse, well, F of inverse of A, and x is in F inverse B. Okay. Um, okay, back, let's make it in this form. So instead of A and, so x is in F inverse A intersection F inverse of B. So since x is an arbitrary element of F of inverse A union B, and then after a little while, we got this x in F of inverse A union F intersection F of inverse of B. So hence, F inverse A union B is a subset of F inverse A union F inverse B. It's pretty basic. So let's go back to the other side. Let's now take any arbitrary x in here on the right hand side. So take any x in F of inverse of A union F of inverse of B. So that means x is in F inverse A and x is in f inverse of b. So f of x is in a, and f of x is in b. So back to the original form, f of x is in a union b. Hence, x is in f of inverse a intersection b. I just realized that the whole this I said is union. So sorry, since it's intersection. So since x was an arbitrary element of f of inverse a union intersection f of inverse b, and then we wrote a little, then we got this result. Hence, f of inverse of a union f uh, intersection f of inverse of b is a subset of f of inverse a union b. So let's call this 2, and let's call this 1. So let's introduce some definition. This theorem, if um, A is a subset of um, B intersection C, and if B intersection C is a subset of A, then A equals B intersection C. This is a theorem. We're not going to prove it. It's pretty basic. And everyone who studied math knows it. So this if we gonna prove anything that is equal, any set that is equal, we're gonna use this theorem. It calls the double inclusion method. We first must prove that this is a subset of this, then go back to the other side and prove this is a subset of this. This is exactly what we did here. We first proved that this is a subset of this, which is 1, and then we proved that this is a subset of this, which is in number 2. So, um, conclusion from 1 and 2 and by the double inclusion method, f of inverse A intersection B equals f of inverse A intersect f of inverse B. And that is the end of the proof. So yeah, I hope you guys I hope you guys enjoyed it. So thanks and goodbye.